In this particular video, I'm going to actually build a face recognition pipeline from the data set available in scikit-learn datasets. So I'll be primarily using support vector machines for this face recognition pipeline, but you can plug and play different classifiers and you can check all the stuff if you want. So let's go through a face recognition pipeline and example in detail using support vector machine classifier. Although you can use other classifiers like knife Bayes, random forests, logistic regression. There are so many others that are available. I'll be just explaining each and every step by using support vector machines, but the other classifiers, they can just be plugged and played here as it is. So let's first fetch some data from dataset packages, datasets, import some real face recognition data, fetch LFW people. Let's say this LFW people, fetch LFW people, that's a function, and that function is available in this dataset module in sklearn. And when you will apply that function will actually give you, for example, faces is fetch LFW people with how many minimum, let's say minimum faces per person. Let's say that is minimum faces per person. Let's say that is 50. So I'm actually loading all the faces. I'm getting all the faces, all the face data with the minimum faces per person as 50. So there may be several people in that data set, but I'm just picking up the ones having minimum faces 50. So there may be some people having 70 faces, some people having 30 faces, and so on. I'm just loading all the, so this is a function that actually loads the data. If the data is already loaded sometime earlier in your computer, it will load from there locally. Otherwise, it will connect to internet and will download the data for you. Let's see this faces object. Let's see what is that. What are different kind of stuff that is available. Let's say faces dot, if you see data, and if you just see shape of that, then the shape of your data is basically, there are 2914 features and there are 1560 samples. If you, for example, see faces dot images, and you just see image number 0, and you just see the shape of that image, that the shape of that image 62 by 47, which means it's a matrix with 62 rows and 47 columns. And that makes sense because 62 into 47, that results in 2914, which is the actual number of features available in the data. So that's the total number of features. Now each and every intensity value is acting as a feature, and we have 1560 total subjects. So let's see what else is available. Faces dot target names. Faces dot target names. What are these? So the target names are basically Ariel Sharon, Colin Powell, Donna Rumsfeld. So these are the people. So let me see how many are these. np dot unique. So let's find out the length of these. So faces dot target names dot size. How many are these? So 12. So we have total 12 classes. So 12 different people. 12 different people, and they have this kind of I mean 12 different people with these class names. One class is Ariel Sharon, another class is Colin Powell, another class is Donald Rumsfeld, and all these classes. George W. Bush and stuff like so. Further, we have another variable target. If we see that target, these are actually the class labels. If we see the targets as unique and p dot unique, these are basically the rather than the class labels written as strings, these are the class labels written as labels. So class 0, class 1, class 2, class 3, and so on. If we, for example, see faces dot target names, what is the target name for class 0? What's the name for that? So that name is Ariel Sharon. What's the target name for, let's say, with code as 4? This one. So it will represent, for example, this one. So that's it. That's one more thing. Let me just draw one of the images. plt dot imshow, maybe faces dot images 0. Maybe it shows up some image. Yeah. So that's the image. This image has a lot of grid on it. The color map is not so great. So let me draw a couple of images, maybe some of the images using subplots, maybe in a better way that you can see in that you can visualize a lot of these in a better way. So let me just, so let's say figure and figure and axis equals to plt dot subplots. How many subplots we are going to make? Let's make 8 subplots by 2 by 4. Let's make these plots. They are just empty. Let's fill these plots. These are 8 of them. So first one, second one, third one, fourth one, and all these plots. These are all empty. Let's fill all of them. So for idx and x idx equal enumerate. What was the variable name that we just created? It was ax. Okay, just flatten ax dot flat, and for this what you do is just ax idx dot imshow what image that you want to show, faces dot images, what image at index idx. What do you want a color map? Well, I want a color map to be grayscale. That has code bone here. So what next? I want to set some axis properties just to not show the grid. So I set the x ticks empty and y ticks empty as well. And maybe I should set some labels. Why not? So x label equals faces dot target names inside faces dot target and at index idx. So yeah, I guess it should show me the faces in a more oh, that is y-dix equals to 0. Yeah, so it has not shown me anything. Why not? Oh, I guess I have to make this figure here again because it actually has no figure to go with. Yeah, so these are basically the face data. So you can see this is George W. Bush, this is also George W. Bush, this is George W. Bush, this is Colin Powell, and we do not have another Colin Powell here. But I have shown you just a few of these. I've shown you. Each of this face is has how many rows? Each of this face has 62 rows and 47 columns. So basically the height of every face is 62 units and the width of every face is 27 units. So that's what the face data looks like. So next, what we really do is we will import some classifier and we will work on face data rather than these images. By the way, these color values, if they are flattened out, then that is there in faces.data variable. So let's import support vector classifier or SVA from sklearn.svm import svc, for example, from sklearn.decompositions import, for example, PCA maybe, and from sklearn.pipeline import make pipeline. Yeah, so let's import these packages and then let's build certain models. Let's say PCA model. Let me build a PCA model as PCA. How many components? Let's say, and components is let me choose the components as 150. Whiten equals true. It's a pre-processing state that standardizes the data to standard Gaussian, and that's it. Let me use the support vector classifier. Let me call that as a PCA model. And let me call as a SVM model as SVC. Might be using kernel as RBF, and maybe we use class weight as balanced. Even if some category has more data, some category has less data, let's use the balanced version of that. And let's say we have our model MDL as make pipeline with PCA model and SVM model, and run it. If make pipeline, oh, I already misspelled this pipeline. Make pipeline, yeah, so it works. So now our model is ready now, but really to check the performance of our model, we really have some unseen data or validation data. So what we really do is we actually split the data into training and test set, or here basically the validation set. So from sklearn.model selection import train test split. Yeah, import that. And then what you do is xtrain, xtest. This should be xval basically, but let me write that xtest, ytrain, ytest equals to train test split, and we will be having faces.data, faces.target, and what is the test size? So the test, what should be the test size? I mean, what should be the split size? Maybe the default split size is 25%. Maybe you want to change that. The split size, the test size is, let's say 0.2. So the training and the test data that is there. Now we will train our model on the training data, and we will evaluate the performance really on the test data. But before that, we really want to know, actually there are a lot of hyperparameters that are involved there in support vector machine. For example, there is a value called C that controls the regularization, and there is a value called gamma that actually controls the variance of this RBF kernel. So there are certain hyperparameters, and we do not know which one is the best. So let's use some grid search method available in scikit-learn to actually find out the best values from coarse to fine refinement. So from sklearn dot grid search, where is the grid search located? Maybe it is in the model selection. It is in the model selection import grid search. Yeah, so in the model selection we have grid search cross validation. So then what we really want to do, we want parameters of this grid that are what kind of parameters? The parameters are in the dictionary form. So we have a dictionary. So the dictionary, what kind of variables you really want for finding out using cross-validation in the grid search. So in SVC function, there is a parameter C. I want that, and I want that to be searched from coarse to fine refinement. Let's say I want it to start from 1, maybe, then maybe 5, then maybe then maybe let's say 15, and then maybe, yeah, maybe let's say 30 or something like so. That's the first argument. And the second argument is, let's say, what other variable you really want to search for. Let's say gamma. That is also, the gamma is the variance or the width parameter of the RBF kernel. So let's have this as, let's say, the gamma values are, let's say, 0.00, maybe 1, then maybe 0.0005, then maybe it is 0.0001, maybe then it is 0.005, maybe like so. So I want this to be searched in a parameter grid. So then what I call is, I make a grid using this function, grid search cross validation CV, and I give my model MDL. My model is already there, and I give the param grid, and param grid is not defined. I guess I have made a spelling mistake as usual. Oh yeah. So now grid is defined, grid is there. Now what next? Let's see how this grid model can be used on the training data. So grid.fit x train y train. It may take a while to do that, so because it is a cross-validation search over a lot of data, so it may take a while to do that, because it is doing a grid search in the best parameter search in the grid we just have defined. So be patient, hold on. It will take a while. It will take a while. Yeah. So basically, I'm pausing this video here, and when the function will return back, I will just restart the video. So hold on. So yeah, so it returns back. It take, I guess, a minute or so to do this grid search. Next, what we see what is the best value of the parameters that we really come up with. Print grid not best params. What are the best parameters that our grid search come up with? So our grid search come up with the best C value is 1 and best gamma value as 0.005. Now we'll be using this particular model. So let me change our model. Let me call my MDL now is basically grid dot best estimator. What was the best model? That's our model. So once now after cross validation, after grid search for hyperparameters, now we have our best model available. Now let's predict the values on the test set. So let's predict the values. MDL dot predict on the test set, and let's see what are these values. These are the values. Maybe we should just see y test. We should just print that, and one way is to just print y test and then print y predict, and just to compare those. That's a bad idea because we are going to compare them one by one and it will take a while. So next what we can do is we can just for example pick some of these images and just plot like in red color. We will plot if the if the prediction is not well, and otherwise it will stay in the black color. So let's just plot these things. So figure x equals plt dot subplots. Let's use how many plots? Let's use maybe let's use 3 by 5, these many. And for idx ax idx in enumerate ax dot flat, what we really want to do is we say okay, ax idx dot imshow x test whatever the x test was, just reshape it into the original size. The original size was, remember, it was 62 by 17, I guess. Show that image in the color map is again grayscale denoted by bone. And next we set some properties. Let's say ax idx dot set x ticks as this and y ticks as this. Now let's set the label in a way that if the target is correct, then the label is in black color or green color. If the target is not correct, then the label is in red color, let's say. So ax idx dot set y label faces dot target names, let's see, y predict, and that is y predict idx, yeah, this much, dot split, just split that in this particular way, -1, and yeah, we are moving on. So yeah, this, and just set the color equals to green if they are equal, if y predict equals to y test at this idx location. If these two are the same, then set the color as green, otherwise set the color as red. So else the color is simply red. Yeah, this. So what next? Figure dot subtitle let's say the size is 14. Subtitles, really I want to do the ax idx imshow. This is not working. Why not? Cannot reshape an array of this into 62 by 17. Why not? What's the original size? Isn't it 17 or maybe something else? Maybe I'm missing. Oh, it's 47. Sorry. Yeah, it's 47. That's my mistake. 47. Yeah, so it's 47, and now we run it. We get this y label function that is going bad. Axis.subplot object has no attribute y label, set y label. So yeah, so what you can do is set, we call the set, and y label, x label is that, and y label equals to this, and invalid syntax. So we got some error here. Let me fix that error here. So there is some yes, this y label spellings were wrong. I just fixed that up offline. I just fixed that up offline. So this spelling was wrong. So I just, because as always I written this spelling, and it was giving me this error, and its spelling is wrong. Yeah. So now, oh, there's something else missing. Oh, subtitle requires a string as well. So let's say wrong or in red. Let's say that's the subtitle. So now all the classifications that are correct, they are in green color, and all the classifications that are wrong, they are in red color. So now we can change that. For example, we can have, for example, maybe just maybe 5 to, let's say 7, and let's see what happens. How many are these here now? Yeah, so a lot of correct, and a few of those are wrong. I mean, this George W. Bush was classified as Powell, that's wrong. This person is classified as Tony Blair, that's wrong. This person is, I mean, but a lot of them are correct. Yeah. So I've just picked the one of, I've just split it and picked the names. Because if I write all the names, they were lengthy, so I call this split function just to pick the splitted version and the after names of these people. Yeah. So I also show you, I also told you that we could have, for example, we could have confusion matrices as well, to rather than visualizing this in that way. Why don't we just find out, why don't we just draw a confusion matrix to see which class actually is confused with what other kind of classes. Further, we can have different accuracy measures as well. So for example, let me import some of this let's say matrix, sklearn dot evaluation matrix, sklearn dot evaluation. So this matrices and all these, so this is located in metric sklearn dot metric. Yeah, sklearn dot matrix, import, for example, classification report. Yeah, if you import that, then you can have a lot of summaries. For example, what kind of so let me print that out for you. Classification report, y test, that y predict, that we just predicted, and what kind of names that you really want to, then the target names is equal to target names is equal to faces dot target names. Yeah. So now with that, you'll be having the full for example, Ariel Sharon has this, for this particular class we have this precision, that recall, that is F1 support, that is support, that is F1 score, that is support, that is the overall accuracy, that's the overall support, and a lot of summaries there. We further can have, for example, confusion matrix for this particular data, just to check which class is confused in which one. Although this classification report is better, but sometimes for classification tasks it is always good to see the confusion matrix. So from sklearn dot matrix, again import the confusion matrix, import confusion matrix. Yeah, so matrix is confusion matrix y test, y predict. That's the confusion matrix. To build a heat map, we already have imported Seaborn, I guess. Yeah, Seaborn is already imported. So let's build a better visualization using a heat map. So heat map, mat dot transpose square, let's say true, just for a better visualization in a heat map. So FMT, the heat values in FMT is in D, and C bar color bar is not available. Let me make the color bar as false. Then we have this X tick labels as faces dot target names. That's the X tick labels. Y tick labels, let me give those as also the target name. So Y tick labels is also the faces dot target names. Hope that I do not do a spelling mistake. So plt dot x label, that's the true label, and plt dot y label, that's the predicted label. So if there is no spelling mistake, I guess it should work. And yeah, oh, how cool is that? That's the confusion matrix for this. Yeah, so basically it is not showing me the y ticks here. Oh, y ticks are also shown here. It's below here. So that's the true label. Let me show you that beautiful plot here. That's the confusion matrix. So Aryan shawl and Aryan shawl, they are just so Aryan, this Arial shawl is confused with this Colin Powell 3 times, and it is confused with Norman Rumsfeld with 1 times, and so on. So that's the confusion matrix, but mostly the matrix is sparse, which means most of the predictions are correct and only few of them are just like so. So that's the confusion matrix. Maybe we for example, maybe we want to play with those. Let's say some of these, but in that case it doesn't show anything. So Control Z. So yeah, so this is basically the confusion matrix. We also have a classification report and all that stuff. Now that was basically the face recognition using a pipeline of PCA and support vector machine. We also use the grid search for the optimal parameters using this grid. Obviously, if we define this grid more, it may take a while, but it will come up with hyperparameters that are good. Hyperparameters are not just these parameters. What model are you using? Whether, for example, you're using SVM, that is also a hyperparameter. You might have used knife based classifier or random forest or something else. But this grid search sometimes help for these kind of numeric hyperparameters to find out, and overall cross validation helps to find out the other kind of parameters, like what model class I'm going to use. Now, if you go and you just change this SVM model with random forest model, for example, or logistic regression model or knife based model, you'll be actually applying this face recognition example on different other models. And all this thing is to just change this model right here, and everything else is as it is, and you're good to go. So yeah, so I wind up this video here. So it was a great experience, and it was a great introduction to all this kind of stuff. I also learned a lot in that course, so I hope for you as well. So good luck.